Alright, so let's go over these now and see what we came up with. So start with the first one, CH4, which you may know as methane. Now, what do you need to do to be able to draw these Lewis structures? Well, one of the ways that we started when we were new at this was we counted up the valence electrons. Carbon has 4 valence electrons. Each one of the hydrogens has 1 valence electron. Since there's 4 of them, we have a total of 8. So we put carbon in the middle, and we draw bonds to each of the hydrogens. So we've used up all 8 of our electrons. Are all of our atoms happy? Does everyone have an octet? The answer is yes. We've used all the electrons, and so we're in good shape here. The problem becomes when you got to number 10, C10H22, if you tried to do that one in this way, how many valence electrons did you come up with? The answer is 62. And can you imagine trying to go about a question like this with 62 valence electrons? I think we all know that would be pretty awful to do. So what we want to start being able to do, especially with these elements that we are going to use over and over and over again, is to be able to take some shortcuts. So let's bring that periodic table back. Hopefully, some of what we remember is the following: the number of valence electrons in each column. Group 14, which has carbon, has 4 valence electrons. Nitrogen's group 5, 6, and 7. And what's our goal always? Our goal is to try and get to an octet, which is 8. So if one of our elements in group 17 wants to form an octet, how many more electrons does it need? It needs 1 more. So how many bonds will it form? In general, 1. Over into group 16. How many bonds do we need? We need 2 electrons, therefore we need 2 bonds. Nitrogen has 5 valence electrons. It needs 3 more, so it's going to in general form 3 bonds. And carbon forms 4 bonds. So does this mean we always form 4 bonds to carbon? Yes, always 4 bonds to carbon. All right, what was our next example on here? Ammonia, NH3. So we can go through the same way that we have and count up the number of valence electrons and draw it out. Or we can just think about the fact that we know that nitrogen has 5 valence electrons and needs 3 bonds. And then the last 2 electrons come in as a lone pair. So right now, it's still okay if you're doing them the way we learned them in foundations. But as we start to do more and more of these, we're going to start to see patterns. And what that means is that we should be able to start doing these without having to draw out every single valence electron each time. Our third example was water. Oxygen, we now know, needs 2 bonds. and then has 2 lone pairs. And then HF, fluorine being group 17, has 7 valence electrons, only needs 1 more or 1 bond. So if you're struggling with Lewis structures like these first 4 especially, definitely something you're going to want to come and get some help with. Because again, these are things that you just, they have to become sort of very, very, commonplace, very straightforward for you to be able to do these. Because eventually, we're going to start dealing with molecules that have 10, 15, 20 carbons. And we want to be able to recognize what's there, what's bonded, what can and can't happen because of the bonds that are already there. All right, 5 and 6, we have a 2-carbon molecule and a 3-carbon molecule. So we're just building up our number of carbons, but nothing all that complicated in either one of these. And here we add a 3rd carbon in. So these are, if you're wondering, ethane and propane. These are names that we will have to learn in the near future because these start to get into the basics of nomenclature of organic molecules. I often tell my students that, by the end of organic chemistry, if nothing else, when you go home and you pick up that, shampoo bottle or bottle of lotion or whatever else you might have where you live, and you see all those weird ingredient names, you'll know what they are. Such as in a case like this. Here's a lot of bits of nomenclature that we might not recognize. Although eventually, you'll know what almost every one of these terms mean. So do you think that's something you'd want to consume? For me personally, no. But for some of you, you may. How about this one? Again, all sorts of interesting names there. Might or might not be something you want to eat. But to me, personally, this is one of my favorite foods. So these are actually a series of posters made by a chemistry teacher in Australia who titled them with the heading, what if natural foods had to come with ingredient lists? But while these names sound very strange and whatever else you might attribute to them right now, by the end of this course, you'll actually understand what almost all of those names mean. But back to our Lewis structures. So we did C2H6 and C3H8. But now we take a hydrogen away, or 2 hydrogens away, and go to C2H4. Well, the only way that we can do that is by sharing even more electrons and giving the 2 carbons a double bond between them. And if we take away even more hydrogen, C2H2, that's going to require a triple bond. So finally, let's get to the last two. C2H6O. So how many of you came up with that one as an answer? Now some of you may have also come up with this one. Is one right and the other one wrong? Well, if we look very carefully at these structures, they both have 2 carbons, they both have 6 hydrogens, and they both have an oxygen. Does everyone have an octet? So all of the carbons have 4 single bonds, so they're happy. All of the hydrogens have 1 single bond, so they're happy. Remember that for hydrogen, an octet is the nearest noble gas, which is actually helium with 2 electrons. And the oxygen here has 2 lone pairs and 2 bonds, so it also has an octet. So both of these are valid Lewis structures for C2H6O. And the problem gets worse when we get to C10H22. I suspect most of you went for the the most straightforward one, which is just a line of 10 carbons. But there's many other ways that we could have drawn C10H22. You're also seeing a good example here of why we will eventually learn what are called line structures, which are a simplified notation for drawing organic molecules. Just takes forever to draw all of these. So that's a valid structure, but you could have easily done something like this. And so I'm going to leave the hydrogens out for clarity, but I will draw just the numbers of them in. Now, if I've done this correctly, that should still add up to 22. And it does. So there's 3 main points that I'm hoping that you take from this. First, hopefully we remember how to draw Lewis structures. Second, we see patterns. So carbon, 4 valence electrons. Always forms 4 bonds. Oxygen has 5 valence electrons. Nitrogen has 5 valence electrons, forms 3 bonds. Oxygen has 6 valence electrons, forms 2 bonds. The halogens have 7 valence electrons, generally form 1 bond. And hydrogen has 1 valence electron, generally forms 1 bond. The third, and these will be true in almost every case. The third item that I hope you take home from this is the chemical formulas aren't sufficient anymore. We saw a structure as simple as C2H6O had 2 possible compounds that we could have drawn. And so this brings us to the idea of what are known as isomers. Isomers are examples of different compounds with the same chemical formula. In other words, we have a different arrangement of the atoms within the molecule. One of the best examples of this, because does that mean that these are completely different molecules? The answer is yes. If we look at the compound C8H18, I'm just going to draw out the carbons. I'm going to leave the hydrogens out. So we're just going to assume that they're there right now. The base name for C8 is octane. So as you might guess, it has something to do with what you might put in your car. Here are two methods for arranging the 8 carbons. So the compound up on top, this is octane, and is something you probably don't want to put in your car. Why not? Well, it turns out octane has a very, very low octane rating. In fact, what is the octane rating of octane? -20. So that's actually pretty terrible for your car. The compound at the bottom is known as isooctane and has an octane rating of 100. So two very, very different fuels. Same number of carbons, same number of hydrogens. The only thing we do is change how they're attached a little bit. So how many isomers are possible for different types of compounds? Well, if we have C4H10, 2 possible isomers. We jump up to 6 carbons, there's 5 possible isomers. Increase to 7, there's 9. So that one I showed you that you did as practice earlier, C10H22, actually has 75 possible isomers that you could have drawn. So let's skip ahead. How about C40, which would have 82 hydrogens? Anyone want to draw all the isomers for C40? Over 62.5 trillion. And if we go all the way up to C100, almost 6 times 10 to the 39th possible isomers. So again, the point here is a chemical formula isn't good enough to describe what we need. And when we're dealing with organic molecules, what we're going to need is either to call it by name or draw out its structure.